Okay, thanks for coming back to my second lecture in this short sauna on optimal transportation and its applications. So my plan is to talk about applications to general relativity and non-trivial geometry today, and applications to economics tomorrow. Most of what I'm going to say is joint work with some subset of Mathias Braun, Mathias Braun, Mathias Braun, Nicola Gigli, Argam Ohanyan, Felix Rod, and Clemens Saemann. So we have an 8 author work that's, and then we have some 5 author works that follow that are all on the arXiv at the moment. And so let's see, there's this general program that's been flying for about 20 years now in geometry, which is to replace, to some extent, to replace smooth manifolds with metric spaces and have notions of curvature, or at least curvature bounds, which work in the context of metric spaces. And so a more recent effort is to try to do something similar in the context of Lorentzian geometry, where instead of a distance between pairs of points, what you have is a time separation between pairs of events that tells you what the maximum amount is you can age is when moving from one event to another. So I'm actually going to focus on some particular topic within this that I think is interesting, which is the splitting theorem. And so splitting theorems are kind of a dimension reduction technique. And so, and they tell you, when your geometry has trivial directions in it. And so the most trivial example I know of this theorem is this one about convex functions, which says that if you have a convex function, n variables, and its graph contains a doubly infinite line, then in fact it's a function of n minus 1 variables. So one direction is trivial. And then a much fancier version of this from the Riemannian world is this theorem of Cheeger and Kolding from 50 years ago, which says, oh yeah, so what's to notice about the trivial? So first of all, I don't care about smoothness of the convex function. So this is a theorem that's potentially adaptable to a non-smooth world. But I do care that it's defined on all of our n. So the Riemannian analog is that if you have a connected complete manifold, which is Ricci non-negative, this is the analog of convexity, and if it contains a doubly infinite line, which is distance minimizing between any pair of points on it, then in fact the geometry is a product geometry of a Euclidean line with an n minus 1 dimensional manifold and the restriction of the metric to that n minus 1 dimensional manifold. And so in particular, you have this isometry where the metric in the empty space factors. So it's not just a topological splitting, it's a geometric splitting. So I would say, oh yes, and in fact the submanifold inherits the Ricci line. And there were earlier versions of this floating around I think in 2 dimensions, going back to Cohn-Vossen, and under non-negative sectional curvature bounds by Toponogov. And there's also a rather powerful extension of this theorem to metric measure spaces, but you need so again, about 20 years ago, Lott, Villani, and Sturm introduced the notion of what it meant to have a Ricci curvature lower bound on a metric measure space. And things like Banach spaces satisfy it, regardless of what norm you put on the Banach space. But to have this kind of theorem, you need a little bit more structure. You need the tangent space to be Hilbert and not Banach. And so Nicola Gigli has this non-smooth version for infinitesimally Hilbertian metric measure spaces, which satisfy the curvature dimension lower bounds of Sturm, Lott, Villani. And these lower bound, they call them curvature dimension conditions. When you have this infinitesimal Hilbertianity, you add this Riemannian curvature dimension conditions. But so how do you define Ricci lower bounds in a metric measure space? The first thing you do is you try to lift the geometry from points in the space to measures, probability measures that live on the space. And you can do this using optimal transport. So you have a distance between points and you want to lift it up to a distance between measures. And then in the underlying space, there's a notion of what it means to have a geodesic connecting 2 points. And once you lift distance up to probability measures, you can define a notion of what it means to have a geodesic connecting 2 probability measures, and what it means to have, say, a lower curvature bound of 0 is that if you along every, if you take any two probability measures, you would like to know that there is a geodesic joining them along which the entropy at the midpoint is no larger than the entropy of the average at the endpoint. So in other words, somehow the picture is, if you have something that's positively curved and you take a probability density sitting up here and you transport it to a probability density down there, you expect it to be more spread out in the middle. That's what Ricci curvature does for you. Whereas if you did the same experiment with a saddle surface in the mountains and you had a probability measure up here and a probability measure over there, and you transport this one to that guy, it's going to kind of focus in the saddle, so it will be more concentrated in the saddle. And this is a sign that you don't have non-negative Ricci curvature. So under this kind of assumption, and with this infinitesimal Lorentzianity, Nicola was able to extend this theorem to the metric setting. And so anyhow, so what I'm going to try to do are talk about some Lorentzian, possible Lorentzian analogs of this kind of developments.
So for this picture, Ricci curvature is the right notion?
Right. So the point is that you have a direction of transport here, and the spreading is basically the amount of entropy that this thing carries. You know, it may be stretched in some directions but compressed in others, but what you care about overall is, say, the change in volume, and that's governed by measure. Thank you. Anyhow, so I'm going to sketch a proof of the Cheeger-Gromoll splitting theorem. So you take your doubly infinite isometrically embedded line. There it is. And the idea is you pick a point that's far away on it, and you want to look at the level sets. I can simple it R. So this is maybe gamma 0. And as this point gets farther and farther away, you look at the distance to this point, and the level set of the distance passes through this. And as that guy goes farther and farther away, you hope it gets flatter and flatter. And you can do the same in the opposite direction. And so the lines that are constant from here are flat. And what you hope is that as this goes to plus infinity and that goes to minus infinity, these two surfaces converge to each other. And then the guy that they converge to is going to be the factor. And you're going to take the product of that with the line. And hopefully that gives you your geometry. So, so you take the distance to this point, but you want to normalize it to not go to infinity. So you subtract off the distance to this point, and you get this function called an approximate Bouzemont function. And the limit, as r goes to plus or minus infinity, you get the limiting Bouzemont functions. And since the distance is a one Lipschitz function, here's the x dependence. These Bouzemont functions all have gradient unit norm. And the same is true of the limits. And then the triangle inequality also tells us that as r goes to infinity, this thing decreases monotonically to some limit. And the negative of the other guy with minus r increases monotonically to some limit. And so this limit is bigger than that limit. And then what we hope is that b plus coincides with b minus. And at least at gamma 0, where these guys intersect, all these Bouzemont functions are 0. The approximate guys and the limiting guys. And so they at least coincide at one point. And so then now there are several ingredients. There are basically 3 heavy ingredients. And one of them is this Laplacian comparison theorem of Calabi. So let me motivate it a little bit. So if I'm in Euclidean space and I look at the distance squared, and then I take its gradient and I get x, and I take the divergence of the gradient, the Laplacian, and I get the dimension. And this is also the distance squared over, sorry. So this is the Laplacian of distance squared over 2, which is also something like distance, Laplacian distance plus a correction, which is gradient distance squared. And so I can also write the Laplacian of the distance as n minus 1 over the distance, where I've fixed some point. So it's the distance to some point. Fixed null, let's say. So this is the story in Euclidean space. And what Calabi-Yau's theorem tells you is that if you're on a Ricci non-negative manifold, then there's a very analogous story, except you get inequalities. So if you look at the distance squared to some point x naught, the Laplacian is going to be less than n. And there's an analog to this guy that says, well, if you use the chain rule, that the Laplacian of the distance will be less than n minus 1 over the distance. And actually, an interesting thing about this paper of Calabi-Yau's from 1958 is he shows that this inequality holds not only where the distance is smooth, but also he has a sense in which it holds across the cut locus, which he calls the support sense, and it anticipates the notion of viscosity solutions from the PDE literature about 20 years later. And so as a consequence of this, if I take gamma r to infinity, the denominator gets large, and I get the Laplacian of B plus is going to be less than 0. So I have a superharmonic function. And because of the minus sign here, the Laplacian of B minus will be bigger than 0. So B minus will be a subharmonic function. And I know they touch here. And so the strong maximum principle tells me that they should coincide. And when you have a guy that's trying to curve downwards and a guy that's trying to curve upwards, and the one is above the other one, they touch, then they have to be equal. And so that's sort of the Hopf maximum principle from the 1930s. So now I know that the limits are actually harmonic and smooth. And then there's one more heavy ingredient, which is this Bachner theorem identity from the 1940s, which again, in Euclidean space, this is, in Euclidean space, if you take the Laplacian of a gradient squared, you get, take the Laplacian of a gradient squared in Euclidean space, I get a term where the derivatives land on separate things here, and then I get a trace of the Hessian squared term. And then I get a term where they land on the same guy, and that gives me an inner product of the direction with the direction of gradient Laplacian. And when I move from the Euclidean setting to a Ricci non-negative setting, there's a correction, or any setting, right? There's a Ricci correction. And so what's the point? The point of why is this relevant? So for these limiting Bousselmann functions, they have gradient norm 1, and so this term vanishes. And they're harmonic, and so that term vanishes. And so the whole right-hand side is 0 for B plus and B minus, which coincide with each other. And the left-hand side is positive definite. And so if the Ricci is non-negative, then this trace, and the right-hand side is 0, then the trace has to vanish, and the Ricci has to vanish. And so then I get not only harmonic, but I get Hessian vanishes. And somehow that's the essential ingredient that tells me, on the one hand, the Hessian vanishing tells me that the gradient of, I guess it's this limiting surface. It tells me that the gradient along this thing is parallel, so that the surface is totally geodesic. And it also tells me that it's a killing vector field. And so if the flow lines of the gradient should give me isometries between this surface and the other level surface of the limiting function, E plus equals constant. And so so the geometry splits into a product of whatever the geometry is on the 0 level surface and the Euclidean line. And so on the 0 level surface, the metric splits into a tangent direction. So then, in fact, the exponential map is surjective, gives you a global isometry. So are there questions? So now I'm going to switch gears and I'm going to talk about Lorentzian geometry for a while, which was the framework for Einstein's theory of gravity. And so it's Einstein's theory of gravity is formulated in this context of smooth differential geometry, but on the other hand, people realized fairly soon, well, that it predicts that the geometry doesn't stay smooth. So for example, you go into the past in a time that you can estimate, you hit a Big Bang singularity, or you fall into a black hole in a time you can estimate, you hit some other kind of singularity, a curvature singularity in the interior of the black hole. Well, okay. Shortly after Einstein, people had exact solutions showing this. And then there was a controversy for about half a century in which some people felt that the singularities were an artifact of the symmetry of the exact solutions. And this controversy was resolved in the 1960s by Penrose and then Hawking, who showed that you don't need, that these singularities are kind of generic. And I'll talk more about those results a little bit later on. But so once again, I assume that most people are not experts on general relativity here, so let me explain the basics. So the idea of the theory is that gravity isn't a force, but rather it's a manifestation of space-time curvature. And the central equation in the, Wheeler summarized this by saying that space-time tells matter how to move and matter tells space-time how to bend. And the central idea or equation in this theory is that things we perceive as physical, namely the flux of energy and momentum in a system, which even satisfy conservation law, are actually manifestations of some curvature in the underlying space-time. And to make this precise, the flux and energy momentum at each point in a four-dimensional space-time are captured in a gadget called the stress-energy tensor. And the basic equation in the theory is that the stress-energy tensor is proportional to the Ricci curvature minus the scalar curvature times the metric. So this is supposed to be a divergence-free tensor because of conservation of energy and momentum. And the Ricci tensor by itself is not divergence-free, but when you subtract this correction, it becomes divergent. And there's a thought experiment that Kip Thorne does when he describes this. He says, suppose you were the captain of a spaceship sent to investigate the geometry around a massive black hole. And so you put your spaceship in orbit around the black hole. And then you gently fire the thrusters to lower the level of the orbit. And long before you approach the horizon or any kind of any hint of singularities, what you start to feel, if you're orbiting in such a way that your feet are pointing towards the black hole and your head is pointing away from it, what you start to feel is that your head and feet are stretched away from each other, and your front and back are compressed towards each other, and your side and side are compressed towards each other. And this is because your head and your feet are both trying to follow geodesics forward in time. But because of the curvature of the space-time, the geodesics they start out parallel, but they don't stay parallel. They try to separate, and that's why you feel stretched. And then in that context, the content of this equation here, if you assume that you and your spaceship are small, are not distorting space-time very much, so that the right-hand side is essentially zero where you are, and all the curvature is being produced by some faraway mass, then the left-hand side has to be zero. So that means, in fact, the Ricci tensor has to be zero. And so the content of this equation in that context would be that the Ricci tensor in the future direction is the average of the sectional curvatures of all the triangles that are comprised of future and some orthogonal spatial direction. So it's the average of the head to foot, side to side, and front to back curvatures. And so those things have to sum up to zero. And so then the quantitative prediction of the theory is that the stretching you feel head to toe is twice as strong as the compression you feel side to side, front to back. By symmetry, front and back and side to side should be the same. Okay, and so this is supposed to be an analog of, this kind of replaces Newton's theory, in which instead of this 4x4 tensor equation, you'd have a single equation that relates the gravitational potential to the mass density, and the force would be given by the gradient of the Newtonian potential. And so if you think about this theory, you're often given the mass and then you solve for the force. And so the analog here would be, if you're given this physical content of the space-time, you can solve for the geometry. But typically you're not given the physical content of space-time. At best, you maybe know that on a hypersurface, which is like a given instant in time, or maybe on the past. And so people that study the initial value problem for Einstein's equation think about the case where you have maybe this and its normal derivative along a hypersurface, and you try to solve for this in the future and past of that hypersurface. And again, although this is a very nonlinear equation for the metric tensor in terms of the stress energy, if you linearize this around a fixed solution, what you get is a wave equation, because the underlying geometry is three directions of space and one direction of time. And wave equations don't have smoothing properties. And so again, that's some intuition for why one shouldn't necessarily expect solutions of this equation to be smooth. And so that's one of the reasons that we're very interested in developing a non-smooth framework for studying gravity. Okay, so now let me say a bit more about what is the underlying mathematics. So somehow in Riemannian geometry, the tangent space is the manifold at every point is a copy of Rn equipped with a Euclidean norm or a Riemannian norm. And so the analog in the relativistic context, the tangent space-time at every point is going to be equipped with what we call a hyperbolic norm. And so you get it by flipping one of the signs in this thing. And notice that to make sense of this, I want, I need V1 to be larger than this in absolute magnitude, but let me take it to be not only in magnitude, but in direction. So let me, Minkowski space, there's going to be a future cone and a past cone, and I'm primarily interested in the future cone. So I want my V1 to be up here and my V2 to the end to be down there. And this gadget here is linear homogeneous of degree 1, just like this gadget. Now it's concave instead of convex, and so I set it to be minus infinity outside the future cone. I could put this light on it and make it a nice convex function, but so because this is concave instead of convex, it satisfies the backwards triangle inequality instead of the triangle inequality. But it's terribly asymmetric. Like if I have one direction where it's real valued in the future, then in the opposite direction is going to be minus infinity. In some directions, minus infinity, both forwards and backwards. Those are the space-like directions. And the guys in the interior of the future cone are called time-like, and the guys on its boundary are called null. And guys such that plus and minus v are both outside of S are called space-like. And so this is kind of classification of vectors, of tangent vectors, and then if you're a curve in the space-time, the curve is called time-like if all its tangent vectors that feature at each tangent space. And so in Riemannian geometry, if I'm on a smooth manifold with a smooth enough metric tensor, you define the distance between pairs of points by looking at all smooth or say Lipschitz curves joining point X to point Y and minimizing the integral of the norm of the tangent vector with respect to this elliptic norm. And actually it doesn't matter, I can take Q to be 1, but I can also take Q to be any power larger than 1. And I get, after I take the Q through it, I get the same answer. And sometimes it's convenient to take Q to be 2. And the analog for this construction in the Lorentzian world is you look at all curves joining X to Y, and then you take this hyperbolic norm. And because it's concave rather than convex, you can take Q to be 1 or any power Q less than 1. And you'll get the same answer, and that thing is called the time separation between X and Y. But this integral only really makes sense if the curve is future directed, because otherwise, what's under here is minus infinity. And I don't want to, yeah. So you take the supremum over all future directed curves, and then it satisfies a backwards triangle inequality for the same reason, because this is concave, whereas that was convex. This guy satisfies a forward triangle inequality. Here's the analog. And this should remind you of the twin paradox. So for the twin paradox, you have one twin that stays in place and another twin that is put on a spaceship and taken far away at a high fraction of the speed of light and then brought back. And when they reunite, it's the twin that stayed in place that aged the most. And so, So the distance between X and Y dominates, the time separation between X and Z dominates the sum of the time separation between X and any intermediate point Y. Okay, so
You don't allow Q equal to 1.
you can allow Q equals to 1, but it's often convenient not to, from the point of view that so you want the minimizing curves here or the maximizing curves here to be geodesics. And when you take Q equals 1, then you can reparameterize it any way you want, and you can destroy the geodesic property. And so it's a convenience to take Q to be strictly less than 1, and then you get the correct parameterization for the minimizers. And so notice, so these are, you can also think of this as kind of a Lagrangian action principle. And the Lagrangian action here that you're minimizing over, if you forget the square root on the outside, it's a convex action. Here I'm maximizing, and so it's concave action. I forget. So it's in both cases I'm doing convex minimization. And so let me introduce the Riemann tensor. So if I take a pair of, switch to it over here, of curves passing through the same point, so I call one of them sigma s and the other one tau t. So sigma equals tau equals times 0. So the Riemann tensor is associated with two directions, or the triangle spanned by two directions. So this is tau dot 0, this is sigma dot 0. And you can do this in the Riemannian world as well, but let me do it in the less familiar Lorentzian world. So let me take both curves to have future-directed tangents and the difference between them also to be future-directed. And then if you can try to compute the time separation squared, a short time later between sigma s and tau t, to leading order, what you get is just given by the hyperbolic norm, the square of the hyperbolic norm. And that's quadratic in s and t. And then because these are geodesics, the only corrections to this up to fifth order are an s squared t squared term, and the coefficient of that is what I would call the sectional curvature in the triangle spanned by these two vectors. And the sectional curvature turns out to be quadratic in the two-plane sigma naught dot tau dot. So there's two copies of s and two copies of t here. And so you can use polarization to get a tensor that depends on four variables, and that's the Riemann tensor. So somehow the sectional curvature measures the first correction to Pythagoras' rule in the Riemannian world. And then so you take traces of the Riemann tensor, like this guy, to get the Ricci tensor. And what that amounts to geometrically is fixing one of the directions and averaging over all the directions. And you can take a second trace to get the scalar curvature. And this is exactly what these guys are the tensors that appeared in Einstein's field equation. And then the other thing that we'll need from time to time is a reference measure for our space, which could be the Lorentzian volume, or it could be weighted by a factor e to the minus v. No. Well, okay. Yes. Sorry. You can polarize the Riemann tensor just using time-like directions, and then you get a multilinear object, and you can insert space-like vectors as well. Okay, so this is my digression into what Penrose and Hawking did, and so I wanted an excuse to introduce so in the metric measure setting, we talked about Ricci lower bounds in terms of entropy. And so the analog in the Lorentzian setting is going to be Ricci lower bounds, at least in the future directions. So that's called the strong energy condition. If the Einstein tensor satisfies these lower bounds, that's called the weak energy condition, even though the weak and the strong doesn't imply the weak. But both of them imply the null energy condition, which asks for a Ricci lower bound for vectors that are parallel to the boundaries, or point along the boundaries of the light cone. And so you can also take a right-hand side proportional to the metric tensor if you want. So you can look at these are Ricci lower bounds by 0. This is a Ricci lower bound by k. And so the Hawking theorem tells you the following. The hypothesis for the Hawking theorem is the strong energy condition, so a time-like lower Ricci bound. And it says, suppose you can find a hypersurface sigma whose mean curvature is bounded away from 0. So that's like this hypersurface. It's a space-like hypersurface, so it's supposed to be it's supposed to represent a given instant in time in the history of the universe. So if the universe is expanding with a bound away from 0 along this instant time, at every point on this instant time, and if you have this ambient lower bound on the Ricci curvature, then Hawking's singularity theorem says that you can only go back a finite distance in time from this hypersurface before you encounter a geodesic that can't be continued. And the distance is estimated in some very simple way in terms of this h. And it's probably h over the dimension minus 1 over h. And there is now an extension of this theorem to a non-smooth setting where we represent this lower bound on the time-like Ricci curvature by lifting the the time separation function from events to probability measures on events and exploring the entropy along that. And so Cavallini and Mondino have used this idea to give an analog of the Hawking theorem in just a set of events equipped with a time separation that satisfies the backwards triangle inequality and which has Ricci lower bounds in this sense. So we call these time-like curvature dimension conditions with curvature 0 and dimension capital N. And there's also in positive signature at about the same time with Annegret Bircher and Kristen Ketterer and Eric Woolger, we proved the analogous theorem, which basically says if you have a lower bound on if you have a subset, a submanifold, a codimension 1 submanifold with a lower bound on its mean curvature, then you can't go too far inside that before you get a singularity. So you can estimate the bound on the radius of the largest ball that fits into your space, is enclosed in your space. And in positive signature, you can actually classify the cases of equality, which we can't yet do in Lorentzian signature. They have to be essentially cones. And so this was the Hawking theorem, which somehow is predicting the Big Bang happened not too far into the past. The Penrose theorem, which was proved a year earlier, is proved under the more physically relevant assumption of just the null energy condition. So the weak energy condition, okay, so the weak energy condition is supposed to be respected by most physical systems, but the strong energy condition, not so much. I mean, so classical physical systems, non-quantum. So the null energy condition should also hold in classical physical systems. And Penrose's theorem says, suppose you can find a codimension 2 compact surface, which is trapped, meaning that light can leave the surface in 2 orthogonal directions, but if the mean curvature is positive in both of those directions, the light is sort of getting focused instead of anti-focused. And you have this curvature condition on the ambient space. And if the ambient space if the cross sections of the ambient space are the Cauchy surfaces, so in other words, what is a Cauchy surface? It's a set such that every time maximizing geodesic intersects the set exactly once. If those cross sections of the space-time are non-compact, then there's a contradiction argument that says that there'll be some light-like geodesic that ends after a finite amount of half-line time. And this guy was extended to smooth manifolds with metric tensors that are not so smooth by Melanie Graf in 2020, so C1. And then using this theory of kind of metric measure spacetimes, Cavallini, Mondino, and Manini have a version which works for C0 metric tensors under various additional hypotheses. Okay, so now I'm going to talk about I'm going to come back to we talked about the Cheeger-Gromoll splitting theorem, and I'm going to come back to the Lorentzian analog of that, which is a theorem conjectured by Yau in 1982 and proved in a series of papers by Eschenberg, Galloway, and Newman under slightly different hypotheses. But so I'm going to assume my Lorentzian manifold is such that I can make a continuous choice of future direction. So that's a topological condition, time orientation. I'm going to assume the strong energy condition, and I'm going to assume that I have a doubly infinite maximizing time-like geodesic. And then finally, I need some kind of completeness assumption on the manifold. And actually, the natural one is what's called global hyperbolicity, which says that a Cauchy surface exists. Yau actually conjectured on a slightly different completeness assumption, which is that all unit speed time-like geodesics admit doubly infinite extensions, which need not be maximizing. And so under this particular thing, time-like geodesic completeness, it was proved by Newman that the doubly infinite line forces the geometry of the space-time to split, which essentially means that the dynamics trivialize. So every instant in time looks the same as every other instant in time. And again, the cross-section will be Ricci non-negative. And it was proved a little earlier if you assume the Cauchy surfaces were compact by Galloway under time-like sectional curvature bounds by Beam-Ehrlich, Galloway, and Mark Worson. And then there's a non-smooth version of this by some of my collaborators in Didier Solis. And then for Ricci curvature bounds under hypothesis A and B global hyperbolicity, it was proved by Eschenberg, and then by Galloway just with global hyperbolicity, and finally by Newman just with time-like geodesic completeness. And so anyhow, so one of the my goal for today's lecture is to lower the regularity on Gij for this result to something like C1, what Graph had in the context of singularity theorems. Right, so we're going to lower it to C1, and we're going to also allow for the possibility that the reference measure is not the Lorentzian volume, but is rather weighted by some exponential factor with a potential v. So then the role of this reference thing is that the hypothesis, the strong energy hypothesis, instead of asking for the Ricci tensor to be non-negative in time-like directions, you ask for the Ricci tensor plus the Hessian of V plus or minus dv tensor dv over n minus 1 to be non-negative in the time-like directions. My convention is that my time-like direction has positive signature, my space-like directions have negative signature, but it doesn't really matter because it's supposed to be a 0 not a theta. Okay, but I'm not gonna, I won't, mostly I'll take V to be constant and won't fuss about the presence of these additional terms in the hypothesis. So I put the slide up again about the proof of the Cheeger-Gromoll splitting theorem. And you can imagine trying to follow Boozlemann's strategy using the time separation function instead of the distance. And you still have reasonable, its gradient will still have magnitude 1 in the hyperbolic norm and so on. You'll still have a triangle, the backwards triangle inequality will give you a relation like this. But where you start to really run into trouble is with things like the Laplacian comparison theorem, because the geometry now is Lorentzian instead of, or Minkowskian instead of Euclidean, and so you don't have the maximum principle. You're working with the wave operator instead of the Laplacian. And so what these Newman and Galloway and Eschenberg had to do was they had to say, well, I'm going to work on let me take a spatial submanifold, try to find a good spatial submanifold to work on, and then do all my comparison principles on the spatial submanifold, and then try to propagate it forward and backward in time. And so our strategy is a bit different from this. And so what we're able to prove is that in this C1 context possibly with the C1D, you take, this is with the quintet, you take this isometrically embedded time maximizing line and you try to define Boozlemann functions. So you look at the time it's the same construction that we did over here. You look at the time separation to point gamma r, plus you add a constant so that it vanishes at gamma 0. And then you take the limits forward and backward in time, but now I need a minus sign or a plus sign because the time separation is asymmetric and I always need to be going from x into the future or from the past to x. I need to embed the minus sign here. And these guys will both be reverse Lipschitz in the sense that the difference between the approximate Boozlemann function at a point in the future minus a point in the past will dominate the time separation between those 2 points. And so their gradients will still have magnitude 1 with respect to the hyperbolic norm. And the triangle inequality will still give me that BR decreases to a limit and minus B minus R increases to some limit. And I actually think the minus sign perhaps should not be here, but okay. And they all are going to vanish at the original point. And so, but what are we going to do for our comparison theorem? Well, in the Riemannian world, it was natural to work with the Dirichlet energy. And the Euler-Lagrange equation for this is the Laplacian. If I minimize this thing. But in the Lorentzian world, this Euler-Lagrange equation, this is going to be the wave operator. And so it's, in the Lorentzian world, it's better to work with the Pth power of the, so this was a Euclidean norm, this is going to be a hyperbolic norm. And the Euclidean norm was convex, the hyperbolic norm is concave, so in the Euclidean world, you might want to take P bigger than 1 But in the hyperbolic world, if you take p less than 1, then you preserve the concavity. And so in the Euclidean world, you minimize the Dirichlet energy. In the hyperbolic world, you're going to maximize this guy. And the Euler-Lagrange equation for this, which is like a p Laplace equation, except with p less than 1, because this is you're maximizing a concave function, I should expect the Euler-Lagrange equation to be given by an elliptic operator. And it's a nonlinear elliptic operator, and here it is. We call it the p-D'Alembertian. And then our claim is that in analogy with Calabi's Laplace comparison theorem, this nonlinear elliptic operator is going to satisfy a bound if the strong energy condition holds, which says that the p Laplacian of the approximate Bousselmann function is dominated above by the dimension -1 times the time separation to the point. And so if I let gamma r go to infinity in the future, the denominator will go to infinity, and I'll get that BR is p subharmonic. And I guess I wrote the definition of this guy with capital V equals 0 or constant, and there would be a weight inside the operator if I was working with non-zero capital. And so we prove this inequality here in the distributional sense, which means that whenever you take a compactly supported smooth enough test function, if you sort of do the integration by parts, then you have the metric inner product of the p gradient of the Bousselmann function and the gradient of the test function is dominated, so the test function should have a sign by the integral of the test function over L. And let me go back to p equals q. This operator is linear, and so it's rather easy to take limits in this weak form of the equation. For my nonlinear operator, I need better convergence properties. I need not only the function to go to the limit, but I need the gradient of the function to go to the limit strongly if I'm going to pass to the limit r goes to infinity in this kind of equation. And the other issue is that although this is a concave functional, it's not uniformly concave. Particularly, the uniform concavity fails along the light cone where the thing under the pth root is going to 0. And in order to apply strong maximum principle, for example, you need to uniformize the ellipticity. And so I need to bound these gradients away from the light cone if I'm going to do analysis with this. Okay, so the D'Alembert comparison was proved in the 8-author paper in the non-smooth setting, so not without necessarily a manifold structure. Then the application was, to this C1 splitting theorem is in the 5-author paper, and that assumes that you have this manifold structure. Right, so, whoops. So I mentioned already that this, when p is less than 1, if I put a minus sign in front, then it becomes a convex Hamiltonian. And it's actually dual to this Lagrangian that I used to define the time separation functions. And dual in the sense that if the reciprocals of p and q sum to 1, then the gradient of h and the gradient of L invert each other. And but notice one of the two exponents will be less than 0, and the other one will be between 0 and 1. And of course, the Hamiltonian and the Lagrangian already have a certain amount of non-smooth built into them when you cross the light cone, because one of them, they both go to, I guess, plus infinity, but one of them goes smooth continuously, and the other one does a discontinuous jump, depending on whether p is bigger than 0 or less than 0. And right, so this is basically what I said. So we're somehow sacrificing the linearity of, we could have looked at the D'Alembertian here, but that wouldn't have been so useful because it's not elliptic, and we're sacrificing the linearity of the D'Alembertian to gain the ellipticity of the p D'Alembertian, p less than 1. And if you want to see what this looks like in coordinates, so, you have this concave Hamiltonian or convex Hamiltonian, depending on your sign. And the operator involves the divergence of the derivative of that Hamiltonian evaluated at the derivative of the Bousselmann function. And so you get the Hessian of the Hamiltonian. By concavity of the Hamiltonian, this is positive definite. And what it actually looks like is the D'Alembertian has 1s in n-1 directions and a -1 in the time-like direction. But then when you go to this nonlinear thing, you correct that with 2 minus p. And so as long as p is less than 1, this whole thing has the same sign as that. But it has this p minus 2 powers of w in front, and so you need to prevent this thing from going to 0 to infinity if you want to uniformize the ellipticity of the operator. So in this sense, there's a point of contact between today's talk and yesterday's talk, in the sense that in yesterday's talk, when we were wanting to prove the regularity of the optimal mappings, the enemy was that the optimal mapping is tangent to the vertical or horizontal, which is the light cone in the geometry the cost geometry that we introduced yesterday. And here the enemy is that the gradient of the Guzman function becomes, sure. So we have our doubly infinite time maximizing line, and we go to a point that's far in the future, and we look at the time separation between some point x and that point, and we subtract a constant. So we're looking at x of L gamma r, and then we subtract a constant, maybe it's minus this plus a constant, which normalizes the difference to 0 here at gamma 0. And the gradient of this Guzman, this is the approximate Guzman function theorems. So the gradient of this Guzman function is 1, but now we want to let r go to infinity. And in Minkowski space, so I have a light cone like this, and the set of things of magnitude 1 are asymptotic to that light cone. They lie on a hyperbola asymptotic to this light cone. And so as r goes to infinity, what I can worry about is that this thing slides along this non-compact hyperbola, and in the limit lands on the light cone, and then I lose the ellipticity. And okay, so then there's already in the work of Eschenberg, they confronted a problem somewhat like this, and what they were able to show was that there's a neighbor. So when you want to prove the splitting, you take some point near this phi, and you look at the geodesic connecting it to this faraway point, and then you let r go to infinity, and you construct a semi-infinite geodesic, which is called an asymptote to this line. And what you'd like to know is that the tangents in these semi-infinite geodesics are still time-like and not light-like. So they stay in some bounded subset of this and don't asymptote to the light cone. And so what Eschenberg showed was that there's some neighborhood of gamma 0 where this will be true. And so in other words, that all of these, so there's, here it's, so I have a Lorentzian manifold, but I need a way to measure distances on it. So classical work of Nomizu and Ozeki says that there's also a complete Riemannian metric on this, which the completeness means that it has the effect of pushing the singularities to infinity in the G tilde metric. And I'm trying to uniformize the smallness of G, which could go to 0 by showing that G tilde is underneath it, provided I put some constant in front. And they show that there's a neighborhood where this is true for all these constants that, for all these vectors along the asymptotes to my original line, normalized. So maximizing geodesic, connecting to gamma r far away, the tangent vector stays uniformly away from 0. Hence, these guys are time-like and uniformly equiliptious, and that tells me the limit is Lipschitz, and that tells me the limit also has time-like gradients. And so a way to understand this Lipschitz estimate of Eschenberg that was simplified by Galloway and Horta later is that, okay, so this is the picture in the G metric, but I also have some G tilde metric whose level sets are hyperbolas. And so then there's some big hyperbola such that if I'm in a neighborhood of this point here, my unit tangent vectors stay in the, ellipse. There's some big ellipsoid, such that if I'm in a small enough neighborhood of this, the unit tangent vectors to these lines stay in the intersection of this ellipsoid with the future of that hyperboloid. And now this intersection is bounded away from the light cone and away from infinity, and that's my uniform ellipticity. Questions? Okay, so this is the most technical. What the fuck, I think. And actually, so they get this equi-Lipschitz estimate on all these Boson functions that allows me to take R to infinity. In the smooth setting, we're able to do one derivative better and actually get an equi-semi-concavity estimate on all of these geodesics, which says that that if I'm looking at any U in the family of Boson functions for R bigger than some capital R. It's the same capital R as up here. And then I say that these guys are semi-concave in the sense that if I take a point X and I exponentiate with respect to the Riemannian metric in any direction from that X and normalize by the Riemannian norm of V, what I get is bounded above. And this is somehow reflecting so in the Riemannian setting, the distance function is defined as an infimum of things. It's the shortest curve. And so you expect it to be kind of it's an infimum, so it should be semi-concave. Here I'm also getting semi-concavity, but it's minus the time separation. And so time separation was defined as the supreme of things. It should be semi-convex with a minus sign. And so this is the thing that in the smooth setting tells us that we have converges not only of BR to its limit, but of the derivative of BR, 0.1 is almost everywhere to its limit, so we can pass to R, we can let R go to infinity in the D'Alembert comparison theorem, and get that the limiting guys have magnitude 1, gradients have magnitude 1 almost everywhere. And we can also pass, we can pass the limit as R goes to infinity in the P D'Alembert comparison theorem to get the limiting guy is P superharmonic and P subharmonic. And we had the triangle inequality told me that one stayed above the other one and that they coincide at this point here. And so a strong maximum principle will tell you these guys are P harmonic. So in the smooth case, it gives these guys are P harmonic, and the semi-concavity tells us that they're C11. And then you could get smoother if you wanted. But so the other ingredient is Bochner's formula, which there's a version of in this funny homogeneity 2p minus 2 is negative. And this, in some sense, goes back to Oda in 2014, but he proved this for general convex Lagrangian Hamiltonian pairs. So we're interested in the particular case where the convex Hamiltonian is this one. The minus sign to make it an infimum. So it looks the following way. So you have the Hamiltonian evaluated at the gradient. And this guy is, the gradient is 1, so this is going to give me 0 for my Boson function when I take U to be my limiting Boson function. And then you have the divergence of the gradient of the derivative of the Hamiltonian evaluated at the gradient. And this is the P D'Alembert equation here. So this is going to be 0 for my limiting Boson function. And you have that these things are equal to something that involves the Hessian of U squared, and something that involves the Ricci tensor in the direction of the Hamiltonian derivative of gradient U. And so this is a time-like direction, so we've assumed this is non-negative. And here we're in much better situation where if we had tried to use, there is a Bochner formula for Lorentzian geometry, but it's not helpful because if you had the metric tensor instead of H here, the metric tensor has a sign. So even if I know this thing vanishes, it doesn't allow me to conclude the Hessian is 0 because I could have positive and negative things canceling each other when I work with a sign metric tensor. But when I have H sitting in here, H was a concave Hamiltonian, and so the Hessian of H has a sign. And so vanishing of this thing forces the Hessian of U to vanish. And you can simplify it by taking the matrix square root of H using the positivity. And so then you get this is the trace of something positive definite. And so the positive definite thing has to vanish if this side vanishes. So since having a sign on the red term tells me that this thing has to vanish, and so I conclude that the Hessian of B equals 0. But I'm not done. So Hessian of B equals 0, you're mostly done. So you have gradient B is again a killing vector field, so it's going to generate isometries of the space. And but you have this problem that you only had this local semi-concavity and local Lipschitz in a neighborhood at this point. And you can do this at other points on the geodesic as well, but what you can worry about is that when you take the envelope of all these neighborhoods, you get something that looks like an elephant, or a snake that swallowed an elephant in the context of the Petit Prince. And that's not, this picture is not so good for us because we really want something like this so that we have a product geometry. And it's no good if the product geometry shrinks to 0 at both ends. It becomes empty in the limit. Okay. And so, okay, you can follow, of course, Eschenberg and Galloway and Newman had this problem as well, and you can follow what they did. But you can also simplify what they did considerably by using optimal transportation ideas. And especially, so maybe I should go back and say, this happy story that I told where I get C11 for free is in the case where the metric is smooth. If the metric's only C1, then you still get equi-Lipschitz. Actually, slightly better, you get equi-super differentiable. But you don't get this equi-semi-concavity. And then you need to work harder. So what you get, equi-super differentiability is enough to apply the strong maximum principle. And what you get is the functions agree in our C1. And then you need to go back, you need to use a little bit of elliptic regularity theory. And when you want to make sense of this kind of Bachner maximum principle, you need to, multiply by a signed test function and throw derivatives on the test function. And it's a little bit delicate, but we are able to, so from C1, we're able to get to W to 2, I think, and that's enough to make sense of this. Makes sense. Right. So how to improve this funny shaped neighborhood to a better shaped neighborhood? So we're going to call, so this is the definition of a complete time-like maximizable line. So the time separation between gamma s and gamma t should be t minus s for every s and t. And if I have some other curve, sigma, like this one, I'm going to call it gamma adapted if the future Bousselmann function, limiting Bousselmann function, and the past limiting Bousselmann function agree on it. And moreover, the difference between that function at the two different points is s minus t or t minus s, just like it was on the original line, for all s small enough. And then there's a little lemma that says when you have these equalities, it implies some regularity on these curves. So first of all, the curve has to be a maximizing geodesic because the B plus was a reverse Lipschitz function, but I'm attaining equality in the reverse Lipschitz bound. And so then it has to be a continuous curve. And moreover, these co-rays, starting at some point over here, the co-ray, right? So if I do any other co-ray at the same point, it has to be tangent to this particular one, and that forces it to be time-like. And so that somehow gives me this condition. And what it gives me this condition, so it says if I have this condition at the start of the asymptote, then I can propagate it along the asymptote, and I have it at later times as well. And somehow that's that tells me that the C1 has beautifully okay. Right, so we get a little more regularity from the fact that the Hessian vanishes, but this also solves the neighborhood problem to some extent. And we can't use the exponential anymore because in C1 geometry, the exponential is maybe defined, but it's not unique. It's not very well posed. So we have to resort to using the gradient flow. From the Hessian of B plus vanishing, we get B plus minus 2. And so the gradient flow, this is a C1 vector field, and this thing is very well posed. And this gives a locally well-defined isometry on this tubular neighborhood. And right, so that's somehow it's an interplay between the integral of this thing, the co-ray construction, the things that you get by integrating this are in fact co-rays and then agree with the sky. And so you get first a topological and then a geometric product structure. And if you have the weight in, you can see the weight has to be orthogonal to the gradient of the one function. So it respects the weight factorizes as well as the metric tensor factorizing. And finally, the connectedness shows that this isometric embedding has to be surjective, so it has to be the whole thing. And then there's this, so a posteriori, this isometry is C2 for the C1 metric tensors. If you have a little bit more regularity of the metric tensor, you get a little bit more regularity of the isometry as well. And then there's this series of papers written in the Riemannian setting that talk about how smooth does the metric tensor have to be in order to get regularity of the isometries. And each of these papers is written because they claim there's an error in the previous paper. So Calabi-Hartmann claimed they're fixing an error in Myers-Steenrod, and Taylor claims he's fixing an error in Calabi-Hartmann. And so we gave our own proof in an appendix, which hopefully, I hope is error-free, also adapting the things to the Lorentzian setting. But you can somehow convert Lorentzian metrics to Riemannian metrics by adding the direction of the time function to correct the one eigenvalue that has the wrong sign. Thank you very much.